Hey everyone, in our previous session we have discussed about a linear regression model. We realized how we can establish a linear relationship between an independent and a dependent variable. The equation for that linear relationship will follow the linear equation, which is y equal to mx plus b. Now by changing value of m and b, we have infinite possibilities to draw straight lines. Let's find out how we can get the best linear relationship among infinite possibilities. When we are drawing a straight line based on the data points, basically by that relationship, all the predicted values will be along the straight line. Here if you see, these black crosses are nothing but the predicted value, and blue dots are the actual data point. So that means by defining a linear relationship between an independent variable and a dependent variable can lead to a number of errors. For example, if you see here, the predicted value is along the green line and the actual value is the blue dot. The error is the difference between the actual value and the predicted value. By this, we can get error for a specific data point. Now, this error can be a positive error or a negative error. If you see here, the predicted value is more than the actual value. We have to find out a straight line or a linear relationship which has minimum errors for all the data points. Best relationship will have minimum errors for all the data points. In order to calculate the total error of all the data points, we will be using mean squared error. Apparently, this function looks very complicated. However, we will understand how easy it is. Let's start with this first. This is nothing but the actual y value, and the y hat is nothing but the predicted y value. So this gives me the error for our prediction. Now this error can be either positive or negative. In order to make it positive, we can square them up, because we know the squared value will always be positive. And as we have n number of data points, and for each data point we will be calculating error, that is the reason we are summing it up from I equal to 1 to n, where n is the number of data points or this blue dot. So it is showing you sum of squared error. This much is nothing but sum of squared error. And as we are getting total squared error, we can divide it by n in order to get the mean squared error, because we have total n number of data points. So this is actually giving you the mean squared error. Hope you have understood how we are calculating mean squared error from this relationship. Now if we take mx plus b as h theta x, where x is the independent variable and theta is the coefficient, by changing theta value we can get different straight lines here. We can replace this h theta x in place of y hat or the predicted value. That is what we have done here. So our equation is now 1 by n summation of I equal to 1 to n yi, which is nothing but the actual data point, minus h theta xi, which is nothing but the predicted value, and we are squaring it in order to get the mean squared error. In linear regression, this function is known as cost function. In general, we represent it as j of theta. That means cost function is nothing but the mean squared error function for a linear regression model. Now what we have to do, our target is to minimize the error. That means we have to reduce the cost function. We need to find out the perfect value of theta in order to minimize the function j theta or the cost function. If we can find out this optimal theta value, then we can easily find out the best relationship from infinite number of possible linear relationships. So this is our cost function, j of theta equal to 1 by n summation of I equal to 1 to n yi minus h theta xi whole square. Now, if we plot this equation, it will be a parabola. If you know, parabola equation format is something like y equal to x square, and you can resemble the cost function with y equal to x square. Hence, if we plot this function, it will be a parabola. Now, what is our target? We have to find out a specific theta value for which the cost function j of theta will be as minimum as possible. In this case, this point will be the point where j theta will be minimum. We have a number of ways to find out the appropriate theta value for this point. One among them is gradient descent. Gradient descent is an optimization algorithm. It is used to find local minima of a function. Remember, it is an iterative algorithm. That means we have to execute the gradient descent function a number of times in order to get the perfect value of theta where j theta will be minimum. Gradient descent algorithm gives us a very intelligent mathematical equation in order to find out the same. The equation is theta nu equal to theta minus alpha into partial derivative of j theta based on theta. Remember, here alpha is a positive constant. We will speak about alpha later. Let's first concentrate what is the beauty of this equation. The meaning of partial derivative of j theta with respect to theta is what is the change in j theta for a small change in theta. Now, for a small change of theta, j theta change can be positive change or a negative change because it is nothing but a parabola. So, if you see here in this position, when we are increasing the value of theta from here to here, the value of j is basically decreasing. That means this part is the negative side where the slope of j theta will be negative always. Let's check the other side of the parabola. Here, for a positive change in theta, your j theta will change positively. That means the slope of j theta will be positive if we change theta positively. That means in case of parabola, there could be two cases. Whenever we are changing theta in positive side, j theta can be reduced or j theta can be increased here. So, slope of j theta can be either negative or positive. Hope you have understood why we have written here that partial derivative of j theta with respect to theta can be positive or negative. Now, let's check positive side first. That means this side of the parabola first. If the partial derivative is positive, then your new theta will be less than the theta because you are reducing a positive value from your existing theta value. So, new theta will be lesser than actual value of theta because we know alpha is a positive constant. Let's check the negative side, this side of the parabola. Here, if the derivative part is negative, then minus into negative value will be the addition of a positive value with existing theta. So, your theta nu will be greater than of your existing theta. Once you have realized this, you will appreciate this gradient descent function because by this, if you choose initial theta here, then as there is a negative slope in j theta, the new theta will be greater than the existing theta. So, obviously, after getting the new theta, new j theta will be somewhere here. As long as your derivative is giving negative result, or in other words, j theta has negative slope, theta will always increase. That means slowly you are coming towards the actual point where we want to reach, which is nothing but the minima of this function. Now, let's check the other condition. For example, your derivative part is giving positive result. That means this side. You have chosen initial theta randomly somewhere here. If slope of j theta is positive, your theta nu will always be smaller than the theta. That means initially your theta was here, your theta nu will be smaller than the theta. Hence, it will come this side. It will always come this side and your theta will move in this direction. In case of negative slope, your theta will move in the positive direction. The same function, if I run multiple times, slowly it is moving your theta value towards the point where you will reach to the minima of j theta, irrespective of your initial theta choice. Always, if your theta value is giving a negative slope in z theta, your theta value will be increased in the next iteration. If the theta value is giving positive slope in j theta, theta value will be decreased in your next iteration. In that way, after a number of iterations, there will be one point when your theta will point here. That means your j theta value will be minimum. Now, I think you have understood how intelligent this small equation is. We will blindly choose initial theta and then we will iterate the same equation a number of times. We are sure that in each iteration your theta will go towards the target value of the theta. It will always work like this, and if we execute the same equation a sufficient number of times, we will subsequently find out a specific value of theta where j theta is minimum, and that is the reason gradient descent is a very important and fundamental equation in whole machine learning and deep learning domain. Now let's understand what is the significance of this positive constant. This positive constant is the step size. Why? Because whatever changes we are getting here, that means for a small change in theta, how much j is changing, we don't want to subtract or add the whole value with theta, because this change can be a very big change. In order to reduce the effect of this derivative part, we are multiplying alpha to it, and this positive constant will have value between 0 and 1. Usually we choose something like 0.01. Alpha is nothing but a learning rate in machine learning and deep learning domain. The popular value of alpha is 0.01, but it depends on your use case as well. Sometimes we may use 0.001 as well. If you choose a very large value for alpha, your algorithm may overshoot the minimum value. Why? Because your step size will be more. So if your step size is more, then there will be one point where you will overshoot the minimum point, and every time it will oscillate like this, something like this. So you will never reach to the optimal position because your step size is fixed and it is large. Now if the value is too small, then what will happen? This convergence will be very slow. So you have to run the algorithm a number of times to converge to this point where the j theta value is minimum. And that's the reason I have written here algorithm may take too long to converge. Let's revisit what we have learned in this session. In our previous session, we have realized what is linear regression, how we are evaluating the linear relationship between independent variable and a dependent variable, how to write some Python code in order to use linear regression model and predict a continuous or a numeric value. We used housing price prediction as an example. In this session, we tried to understand the math behind linear regression model. We tried to focus to understand how linear regression model internally coming up with the best relationship from given data points. We realized what is error, how from this error equation we are creating the mean squared error, which is nothing but the cost function in case of linear regression model. So now if someone is asking you what is the cost function in linear regression model, you know how to evaluate it. We have also realized that if we can reduce the cost function as much as possible, we will get the best relationship. Now we know if we plot the cost function of linear regression, it will be a parabola, and in this parabola we have to find out the minima. Now there are a number of algorithms for it. We have realized the very basic and effective algorithm what has been used throughout the machine learning and data science domain, which is nothing but gradient descent. We know how gradient descent equation is intelligent enough to identify the optimal value of theta where the j theta will be minimum. We know what is this positive constant alpha. This is nothing but the learning rate. Now, how to choose learning rate? The range is 0 to 1. We are using learning rate to reduce the effect of derivative value in theta. Usually we choose 0.01. If the value of alpha or the learning rate is too large, it will overshoot, it will not converge to the minima. If the value is too small, it will take a lot of steps to converge to the lowest point of j theta. Now you know how linear regression is working internally when we are just importing sklearn library and creating an instance of linear regression model. Basically, that linear regression model is using all these mathematical functions in order to find out the optimal linear relationship between an independent variable and a dependent variable. Hope you have enjoyed this session and you realized these equations are not too hard to understand. Thanks a lot for watching this video.